So hello everyone and welcome to this class. Today we are looking at linear programming, which as we have said, is a topic in operations research. And as we have said, in operations research, we deal with allocation of scarce resources with some objective. And most of the cases, the objective will be either to maximize profits or to maximize profitability, let's say production, or to minimize losses or costs or wastage and so on and so forth. So the name linear programming is coming from these two words, the word linear, then the word programming. The word linear here means the relationship between or among the variables is linear. In other words, there is a straight line kind of relationship among the variables. So we'll be dealing with straight lines in a way. Then programming, of course, means it's like the plan. Okay, it's like the process determining a particular program or action plan. So basically, that's what linear programming will be all about. So we'll be dealing with some linear functions or linear equations or linear inequalities to come up with some plans to either to optimize some chosen processes. Now we'll be dealing with what we call linear programming models. And a linear programming model has the following format. Number one, it has what we call an objective function. It has what we call an objective function. Okay. Then we also have what we call resource constraints. Resource constraints. And then we also have what we call the non-negative resource restriction. Let's call it restriction. So an LP model will have those three parts. It will have the objective function, it will have resource constraints and non-negative restriction. Okay, so you've seen the format, how mathematically we can express this linear programming model. So I'll not be repeating myself in this class. So what I'll do, we'll just do it practically and see basically what happens. So what is the procedure? The procedure of coming up, or let's say formulating an LP model. What are the steps that you follow for you to come up with an LP model? And the first thing you do is to define what we call decision variables. Define the decision variables. Then after that is when you define your objective function. You define the objective function. So here you say what will be maximized or minimized. And you write this in form of some function. Okay, usually a straight line kind of function. It's an equation. Okay, so the decision variables are the x's. So you can have x1, x2, all the way to xn. So if you have two decision variables, you just have x1 and x2. Then your objective function, if you have two variables, will be something like this, like a of x1 plus b of x2. Okay, so but if you have n of them, it will go all the way to plus, let's say n. Let me rename to make it easier. So this is a1, a2, all the way to an of xn. So your objective function will look like that. So either maximize or minimize some function of x, where x is the decision variable. Then after you define your objective function, the next thing is to define a set of constraints. define the set of constraints. And these are either inequalities or equations. Most of the cases are inequalities, meaning that you represent them using that, or that, or this. You represent them using inequalities or equations. Mostly they'll be inequalities. Then finally, you define the non-negative. You define the non-negative constraints. And this basically means that you set the decision variables. You set the decision variables to be non-negative. To be non-negative means to be greater or equal to 0. So each of these variables that we define here cannot be negative. Cannot be negative. So how do we formulate? If you're given a problem, how do you formulate an LP model? So let's have an example. Formulation of an LP model. We're going to have the following example. So let's look at this question on the formulation of an LP model. You're given the following information. A company manufactures 3 products, A, B, and C. The profits are 3 shillings, 2 shillings, and 4 shillings respectively for the 3 products. The company has 2 machines, machine 1 and 2. And in the table below, you are given the required processing time in minutes for each machine on each product. So here's the information. Here's the information on the processing time for each product on each machine. Then you're further told that machines 1 and 2 have 2,000 and 2,500 minutes respectively. In short, these 2 machines can run for the indicated number of minutes. Then you're told the company must manufacture 100 units of A, 200 units of B, and 50 units of C, but not more than 150 units of A. The question is, find the number of units of each product to be manufactured by the company in order to maximize profits. But in this question, we'll not be trying to find the number of units. We'll just formulate the LP model and then we stop there. The solution will come later. So if you're given such a question, how do you proceed? Solution. The first thing is to define your decision variables. And what are your decision variables? These are your decision variables. These are your decision variables. What we are looking for. Okay. And since we have 3 products, we are going to have a decision variable for each of the products. So we say, let X1 be the number of units of type A produced or manufactured. So, that is unknown. From the word go, we don't know that. And the question is to find out their value. How many should we produce of type A and of type B and of type C to maximize profits? Then we also have X2, which is the number of units of type B manufactured. Then finally, we also have X3, which is the number of units of type C manufactured. So those are our decision variables. That's the first step. Then the second step is to define our objective function. And objective functions are of two kinds, either maximization or minimization. So it is the question that we are solving that will tell you whether you are dealing with a maximization or minimization kind of problem. And here we are told maximize profits. So usually we represent the function of profits by letter Z. So we say, first we say maximize. Maximize Z. And then Z is a mathematical function which tells us how much profit we're going to make. So if you're going to produce X1 units of type 1, I mean of type A, and X2 units of type B, and X3 units of type C, it means that the total profit we get from type A, the total profit that we'll get from type A is the profit per unit of type A times the number of units produced of type A. And from the stories, we are told that the profit are 3 shillings for type A products. And then we are saying we are manufacturing X1 of them. Then the profit for type B products is 2 shillings. And we are manufacturing X2. That's a number. And then for type C, we are manufacturing X3. And each one of those will be giving us 4 shillings. So the total profit will be given by this formula here, 3x1 plus 2x2 plus 4x3. So this is the formula that will give us total profit. So usually this function here, it gives us total profits or total loss, or whatever we are trying to optimize, we get the total of it. And we just multiply either the profit or the loss per unit times the number of units to be produced. That's what we have done here. So that's the second part. Number 3, we define our resource constraints. Resource constraints. And resource constraints are usually in form of inequalities, though sometimes they can be equations. So when you look at this problem here, we need to identify which resources are we dealing with here. Remember, we said that the resources include the 4 M's. We also have time and space, where the M stands for manpower, machines, materials, and money. So looking at this problem, clearly you see that we have some machines somewhere. And those machines are, of course, coming with time. Okay. Then we also have another requirement here, the demand. We have a demand constraint here. The units required is also a constraint because we must, okay? The company must manufacture. That means you can't produce less than 100 units of A. We cannot produce less than 200 units of B. We cannot produce less than 50 units of C. But again, we cannot produce more than 150 units of A. So those are the demand constraints. So here, our constraints will have one for the machines. We have constraints for the machines. We are told that the first machine can only run for 200 minutes in total. Okay. Then the second machine can run for 2,500 units. So maybe this one I should have, yeah. Available time. Available time for machine 1 2,000 minutes. And this one is 2,500 minutes. Those are the constraints that we have. We know that every unit of A uses 4 minutes of machine 1. And sorry. And every unit of B uses 3 minutes of machine 1. And every unit of type C uses 2 minutes of machine 1. So the total time used to produce A, B, and C on machine 1 should not exceed 2,000. And we have said that we are producing X1 units of type A, we are producing X2 units of type B, and we are producing X3 units of type C. So what is the total time used to produce all the products on machine 1? It will be 4x1 plus 3x2 plus 2x3. When you sum up that amount of time, should not exceed this much. In a similar way, we have for machine 2. So as far as the machines are concerned, we shall have 4x1 plus 3x2 plus, how many units are here? These ones are 2, plus 2 units of x3. Okay, so that time should be less or equal to 2,000 minutes. Should not be more than that. In a similar way, for machine 2, we have 2x1 plus 2x2 plus 4x3, which must be less than 2,500. So in terms of machines, those are our constraints. Those are our restrictions. Those are our resource restrictions. In terms of demand or production, because you cannot produce indefinitely, there must be some controls. Okay, so in terms of demand, we are told that the number of type A units must be at least 100. But again, we're being told here, they should not be more than 150. So that means we are saying that X1 should be greater or equal to 100, but less than or what is the question here? We're told no more than 150. So less or equal to 150. So X1 should be within that interval. And what about X2? We are told that X2 must be greater than. So we must manufacture 100 units of A, 200 units of B, and 50 units of C. So X2 must be greater or equal to 200. And in a similar way, X3 must be greater or equal to 50. I hope these are not confusing. Huh? Okay. Yeah, because these ones can as well be written as these two. This is the same as X2 is equal to 200. This is the same as X3 is greater or equal to 50. Okay, so it's only that I wanted to use the inequalities facing this direction. So this just means that X2 is greater than 200. The same way you have 3, if you have 3 is less than 7, you have something like that. This is the same as 3 is less than 7. 3 is less than 7. But if you read it in this direction, but if you read it in the reverse from 7, starting from here, you will say that 7 is greater than. You cannot say 7 is less than 3. Is greater than 3. Yeah, this case. So the same. Those stories are just the same. So that is our third part. So those are the resource constraints. Then lastly, but not the least, is the non-negative restriction. Non-negative restriction. And this requires that the decision variables must be non-negative. Non-negative means that they are either 0 or positive numbers. And these are usually you present that. You say x1 is greater or equal to 0, x2 is greater or equal to 0, and x3 is greater or equal to 0. That's what we call the non-negative restriction. So now we have formulated an LP model or linear programming model for the question that is given up there. So let's summarize that story. Let's summarize that story. We say in summary, this is how the model like. So this is how an LP model will look like for the above problem. Okay, so this is now what we are calling an LP model. We said it has three parts. It has the objective function, it has the resource constraints. So that's the first part. This is the second part. And then we have the last part there. Three parts of the LP model. So after you do this, basically the other step is to solve it. Once you have the model, the next thing is to solve it. And once you solve the model, you look for the optimal solution, which you'll be doing a little bit later. Okay, any question there? So let's look at the second example on the formulation of an LP model. And we are given this question here. A home decorator manufactures two types of lamps, A and B. Both lamps must go through two technicians, that's the cutter and the finisher. Lamp A requires 2 hours of the cutter's time and 1 hour of the finisher's time. Lamp B requires 1 hour of the cutter's time and 2 hours of the finisher's time. The cutter has 104 hours, while the finisher has 76 hours of available time each month. The profit per lamp is 6 shillings and 11 shillings for type A and type B lamps, respectively. Assuming that he can sell all the lamps produced, how many of each type of lamp should be manufactured to obtain the best return? So that's the question that we have. So solution, say that before you do anything, you must write your decision variables. What are we looking for? So we are producing two products. So that means we are going to have two decision variables. So we can call one of them X1. So we can say let X1 be the number of type A lamps produced. And of course, we are talking about the number of type A lamps produced, maximize profits or for the best returns produced. Then X2 to be the number of type B lamps, produced for the best returns. So X1 and X2 are unknowns at the moment. So usually decision variables are unknowns, which we must, at the end of the day, we must find their values by solving the model that we are proposing here. So after the variables, the next thing is to define the objective function. Okay, and the objective of this question, what are we given in this case? We are given profit per unit. So that means we want to maximize the profits per unit. So here, this will again be a maximization type of problem. So we maximize. And here we write down a function of total profits from the information given. We are told that we are producing, so we're saying that we are producing X1 units of type A, and the profit for each of these units is given here. The profit per unit of type A lamp is 6 shillings, and the profit for type B lamp is 11 shillings. So the total profit obtained after selling all the lamps produced will be 6x1 plus 2. So the objective function is a function that gives us either total profits or total losses or total wastage and so on and so forth. So that's number 2. Number 3, resource constraints. So which resources do we have here? So it's good to try and summarize the information given so that you can see the resources clearly. So let's come up with a table here. We have the lamps. These are the products. We have lamp A, lamp B. Then we have the human resources. We have the cutter. We have the cutter. And we also have the finisher. We have that. Then we also have available time, one of them. And then here we can have unit profit for each product. So we're having a table like that. So we are told that product A requires 2 hours for cutting and 1 hour finishing. That story is given up there. Okay. So lamp A requires 2 hours of the cutter's time and 1 hour of the finisher's time. Then lamp B requires 1 hour of the cutter's time and 2 hours of the finisher's time. So that means we can have here, what do we say? 1 hour and 2 hours there. Then how much time is available for cutting? So we are told that the cutter has 104 hours available and the finisher has 76 hours available. So that's what we have at our disposal. So this is 104 and then this one is 76. And what about the profit per unit? Each lamp of type A, the profit is 6, and each lamp of type B, the profit is 11. So we have summarized all the information in that table. So all the information given is now captured there. So with this, we're able to know the kind of equations and inequalities that we need. Okay, so let's start with the cutter and finisher. The cutter and finisher, we know that the available time should not exceed 104. So every unit of type A requires 2 hours on the cutter, and every unit of type B requires 1 hour on the cutter. And we are producing X1 units here. So total time there is 2X1, and here we are producing X2 units. So the total time there is X2. So total time on the cutter for all the units produced will be 2X1 plus X2. And this one should not be more than, you can't spend more than 1 or 4 hours. That is the cutter. And the finisher, the same. So every unit produced of type A requires 1 hour on the finisher, and every unit of type B produced requires 2 hours on the finisher. So in total, type A, lamp A will require X1 hours. That is 1 times X1. And lamp B will require 2X2 hours on the cutters, on the cutter machine. And that total time will not exceed 76. That total time should not exceed 76. Okay. And you realize that those are the only resources that we have: cutting time and finishing time. There is no other. In the earlier question, there was an issue of demand. Here we don't have that. So here we're only we are only having one resource, the machine. That's the cutting machine and the finishing machine. So once we are done with that, we need now to write down our non-negative restriction, non-negative constraints. This just means the decision variables are non-negative. So x1 and x2 are greater or equal to 0. Okay. So in summary, this is the model that we are coming up with. The objective function, which is maximize z, which is equal to 6x1 plus 11x2. You do that subject to the first resource constraint is 2x1 plus x2 less or equal to 104. Then we have x1 plus 2x2 less or equal to 76. Then we have the non-negative constraints, x1 and x2 are non-negative. So that is the LP model. That is the LP model. See the three parts: the objective function, resource constraints, non-negative restriction. Okay. So let's look at that. If there's any question, please let me know. So next, after formulating the LP model, the next step is to solve the LP problem. And there are various methods of solving an LP problem. We have the graphical method, the simplex method, the big M method, and the two-phase method. In this class, we shall restrict our discussion to the graphical method only. And one thing you need to note is that the graphical method is only suitable for problems with two decision variables only. So if you have more than two decision variables, it means that you can't use the graphical method. So that means you may want to explore other methods. But as I explained, is that in this class, we're only required to solve LPPs graphically. So what are the steps that you need to follow to solve problems graphically? So the steps are as follows. Number one, the first thing is to formulate the problem into an LP model. So the first thing is the formulation of the LP model. That's what we were doing earlier on. The second step is to consider each inequality as an equation. Consider each inequality as an equation. This is under the constraints. So basically what happens there is you relax the inequality. You relax the inequality, then you draw an equation to represent the resulting equation. Then number three, you plot each equation. You plot each equation on the graph. Let's say on a graph. And you'll notice that each one of them will be a straight line. Remember, we're dealing with linear programming. So that means that we shall be dealing with straight lines only. Then after that, you are supposed to shade appropriately on, let's say that, leaving the feasible region and shaded. So you shade, and usually this happens, so usually this kind of plotting in number 3 happens on what we call the first quadrant. Happens on the first quadrant of the Cartesian plane. You know, when you are plotting a graph, when you're drawing a graph, there are these 4 regions. So let's say this is x1, and this is x2. This is the 0. This is the origin. Okay. So all the plotting happens on this quadrant, this one. Because this is where all values of x1 and x2 are non-negative. So non-negativity is satisfied on this quadrant. If you come here, you find that x1 is positive, but x2 is negative. And already we have said that the decision variables must be non-negative. If you come here, you'll find that both x1 and x2 are negative. And if you come here, you realize that x2 is positive, but x1 is negative. So to make sure that the non-negative constraint is satisfied, we plot on the first quadrant here. We plot on this space. We draw the lines on this space. We draw the lines in this space. Then you shade appropriately. You leave the feasible region unshaded. Okay, you shade everywhere else except where all the constraints are satisfied. Sometimes you will see that there are people who do the other way around. So they shade the feasible region. So either way, but in our case, we shall adopt you shade everywhere except the feasible region. Okay, so so let's have some example to illustrate that. So let's consider the following LP model, and we are required to solve it graphically. Maximize Z equal to 3x1 plus 5x2, subject to x1 plus x2, x1 plus 2x2 is less or equal to 2000. Then we also have x1 plus x2 is less or equal to 1500. X2 is less or equal to 600. Then a negative constraint is that x1 and x2 are both greater or equal to 0. How do we solve this solution? So basically what we'll be doing here, we will be plotting all the constraints. We want to represent this graphically. So that's what we represent graphically. Those are the resource constraints plus the non-negative constraints. And the starting point is you pick every inequality and you convert it into an equation. Okay. Then you draw the line that comes out of that equation. Then you shade appropriately in such a way that the inequality is satisfied. So let's start with the first one. X1 plus 2x2 less or equal to 2000. We convert into an equation. So we end up with x1 plus 2x2 is equal to 2000. Relax the inequality like that. Then you draw the line, a straight line, which represents this equation. You all know that for you to draw a straight line, you need just 2 points. Okay, so we'll choose some convenient points. So we need x1 here and x2 there. We need good points to represent that line. And a good starting point is to set x1 to 0. And also you also set x2 to 0 on the other side. So when x1 is 0, that is if you put 0 here, then the value of x2 will be 1000. Just solve it. We're saying that if you have, this is x1 plus 2x2 is equal to 2000. If you put 0 there, we're left with 2x2 is 2000. Divide both sides. So you get that, huh? And we're also saying, suppose now you put this guy to 0. If you put x2 to 0, then the value of x1 will be 2000. So the points on that line, the points are 0, 1000. That's the first point. And the other point is 2000, 0. So this line here is passing through those 2 points among many other points. Okay, so that's, we'll be using those 2 points to draw that graph. We go to the second equation, the second inequality, which is saying x1 plus x2 less or equal to 1500. So when we relax inequality, we end up with x1 plus x2 is equal to 1500. Similar way, we need 2 points through which this line passes. So we have x1 and x2. We set this guy to 0. If we set x1 to 0, then x2 is 1500 as well. If we set x2 to 0, x1 is also 1500. So this line is passing through 0, 1500, and also through 1500, 0. Okay. Then the third inequality, x2 is less than or equal to 600, less or equal to 600. So if you relax the inequality sign, you will end up with x2 is equal to 600, which you don't need a line on, you don't need the values of x1. You just need to draw a line where x2 is 600 throughout. So that is straightforward. Then number 4, the non-negative constraints, you can ignore them, but you can just say that x1 is greater or equal to 0, which means if you relax it, you get x1 is equal to 0. So you know that line. Okay, a line where x1 is 0 throughout. That's a vertical line which is passing through the origin. Okay, then we have x2 greater or equal to 0, which means that x2 is 0, which is a horizontal line which is passing through the origin. Okay, so let's draw the graph. Let's draw all these lines on on a Cartesian plane. So I want to draw them here. So we have already obtained the points through which all the lines are passing. And now we are starting to draw the lines. And we are drawing the first line. The first line is x1 plus 2x2, which is passing through the points 0, 1000, which is here, and through the point 2000, 0. So this is a line. But we want, this is supposed to be an inequality. The inequality says we want to mark less or equal to 2000. Less or equal to 2000. So we either shade the upper side of the line or the lower side of the line. But we do that in such a way that the inequality remains true. So this is the inequality we have. x1 plus 2x2 is less or equal to 2000. So we either shade the lower side or the upper side. So you can try and choose a point below the line, a convenient point below the line, or maybe a convenient point above the line, and you put it here. And you check whether the inequality is true or not. And I prefer to choose the point 0, 0, because this point 0, 0 is below the line. So if I put 0, 0 here, I will have 0 plus 2 times 0 is less or equal to 2000. which is the same as 0 is less or equal to 2000. And clearly, it is true that 0 is less than 2000. If you pick a point above here, a point which is up here, let's say we pick a point like 2000. Let's say if we pick this point here, if we pick the point 2000, 1000. If you pick 2000, 1000, you'll have 2000 plus 2 times 1000 is less or equal to 2000, which will give you 4000 is less or equal to 2000, which doesn't. This is not true. So for any point which is above the line, the inequality is not satisfied. So we shade there. So that is the unwanted region. So we are shading the unwanted part. So we shade the unwanted part like that. So the lower side is true. So we keep it unshaded. That's the required region. We do the same for all the other equations. So for line 2, we are plotting 0, 1500, and 1500, 0. So 0, 1500 is a point which is here, and the other point is here. We connect those two using a straight line. We connect those two using a straight line, and then we shade accordingly. Okay. So that is the line x1 plus x2. That's the line, is equal to 1500. But now we are working with an inequality, so we want to shade appropriately such that this inequality is satisfied. Usually for convenience, just pick the point 0, 0. If that point is true, you shade the other side. You don't have to use 2 points. So if you pick the point, this is the inequality, less or equal to 1500, then you put 0, 0. So this will be 0 plus 0, less or equal to 1500, which is true. It is true that 0 is less than or equal to 1500. So you shade the other side. So I'll keep shading in black. So I'll shade the area above. So this area does not satisfy that inequality. Everywhere they shaded. Everywhere they shaded. So those are the first two resource constraints. And that's all about the resource constraints. No, I think there's another one. There's this one, sorry. Which says x2 is 600. So you need to go to the axis, which we are calling x2, and you mark the point 600. So x2 is our vertical axis. X2 is our vertical axis. So let's locate the point 600. Let me zoom. So every point here represents 100. So 1, 2, 3, 4, 5, that's 500. So 600 is here. 600 is this point of green, the green point now. So we are drawing a line which is passing through all the points where x2 is 600. And that will be a horizontal line. That will be a horizontal line, which is passing through the point 0, this point here. So it will be a line like that. So any point on that line, x2 is 600. Any point on that line, x2 is 600. But now we need to shade. So where do we shade? The inequality in question is x2 is less or equal to 600. So if I pick my favorite point, 0, 0, the value of x2 will be 0, which I'm saying is less than 600, which is true. That means to shade the upper side. You shade that side. That side doesn't satisfy the inequality. So we can call this as x2 less or equal to 600. So those are the resource constraints. The other two constraints, the non-negative constraints, are easy to deal with, these two. Because this line here, x1 is equal to 0, x1 equal to 0 is the vertical line. This vertical line here is the one that we call x1 is equal to 0. And this horizontal line here is x2 is equal to 0. And all the time, you shading these two, this shade below, and you also shade here. Okay, so line here is x2 is greater or equal to 0. And this line here is the same as 1 is. So now we end up with region here. So everywhere is shaded. Everywhere is shaded. So we end up with this here. R, which is called the feasible region. R is called the feasible region. This is the region where all the resource constraints are satisfied. This is the region where we find the optimal solution if it exists. The number of units of type 1 and type 2 that needs to be produced must be a number within this region here. Okay, so we mark all the points where 2 or more lines intersect. We mark all the points. Let me zoom it. We mark all the points where 2 or more lines intersect, like that. And then we can call them, we can label them. We can label them A, B, C, D. I'm not so sure whether this is 1 point or these are more than 2 points. You can always solve some of these lines simultaneously and check whether it's giving you 1 point. It's possible that this is just 1 point, but it looks like there are 2 points. We can verify that. Yeah, so after plotting the points, after drawing the graph, we identify the corner points. These are the extreme points. We have labeled them A, B, C, D, and E. Sometimes the graph may not be very clear which point this one is. So if that is the case, you solve this equation and this equation simultaneously. Then you get the values of x1 and x2. But I think on our graph it is clear. The same case to this point here. If it's not clear, you solve this equation. That is this equation and this one, which can be done very quickly because now you'll be solving one of the equations. X2 is 600, and the other equation would be this line here, which is saying x1 plus 2x2 is 2000. So of course you have this. So once you plug it in here, you notice that x1 is 800 in that case. So clearly this point here, this must be 800, 600. Okay, and you can do the same for the other two. So those corner points are summarized here. So point A is the point 0600. That is easy to see here. Then we have B, which is 0, 0. Then we have C, which is 1500, 0. Then we have 1500. And then finally we have 800 and 600. So the last thing is to obtain the value of Z. This is the objective function. Objective function value. So remember our objective function was we want to maximize 3x1 I want to maximize what? 3x1 plus 5x2. So we substitute these values into this equation and see what value we get. So if we put 0 here and we put 600 here, we'll get, the first one will give us 3000. So that is the value of the objective function. If you put 0 here and you also put 0 there, this will be 0. If you put 1500 here and you put 0 there, this will be 4500. If you put 1000 here and you put 500 here, that will be 5500. And finally, if you put 800 here and you put 600 here, you will get 5400. So these are the values of the objective function based on the extreme points. The extreme points, one of the extreme points is usually the optimal solution. One of the corner points is usually the solution that we are looking for. And because our objective is to maximize profits, and these are the profits now, these are the profits. So you look at these, a profit of 3000, a profit of 0, a profit of 4500, a profit of 5400. That means maximum profit is obtained here. So this is the combination of resources that will give us maximum profit. So we say that profit is maximized. So the answer to our question is that profit is maximized when 1000 units of what? Of X1 and 500 units of X2 are produced. Okay, so here I'm assuming that this is a product, and this is the other product. So if you produce 1000 units of the first product and 500 units of the other product, that's when you will maximize profit. And the maximum profit will be 5500. That is the solution to that LP model or LP problem. So let's move on. After obtaining the optimal solution in of an LP model, sometimes you may be asked to calculate the slacks, the surpluses, and shadow prices. So as you've seen in the notes, we have what we call slack variables, and we also have some other type of variables known as surplus variables. Usually these are denoted by letter S on the LP model, and a slack variable is a variable which is added to a resource constraint, is a variable that is added to a resource constraint to convert a less than or equal inequality, to convert such an inequality into an equation. as you've seen, when we were solving the problem graphically, we were relaxing the inequality. Of course, that relaxation is only true when you try and either add up something on the left-hand side or you take away something on the left-hand side. Okay. Talk about a surplus variable. These are variable which is subtracted from a resource constraint. It is subtracted from a resource constraint of greater than or equal type to make it an equation. Make it an equation. Okay, so these slack variables are also supposed to be non-negative, just like the other variables, and they are not supposed to change the optimal solution. They are not supposed to change the optimal solution. So once you introduce the slacks and the surpluses, you end up rewriting the model into what we call the standard form. Standard form of an LP model. So the standard form does not have inequalities. So you relax all the inequalities, but you don't just relax them, you introduce slacks and surpluses. And this is what you'll end up with. So let's consider our previous model. And our previous model was looking like this. It was saying maximize Z, which is equal to dx1 plus 5x2, subject to, we're doing this subject to some inequalities here. We have x1 plus 2x2 is less or equal to 2000. And then we have x1 plus x2. X1 plus x2 is less or equal to 1500. Then we have x2 less or equal to 600. So unfortunately here we do not have any inequality which is of the greater than type. So all of them are less than. But I'll show you another example where we have a mixture of inequalities and possibly even when we have an equation. So this is the form that we had our model in. So if you want to convert this into standard form, you introduce slacks, and those slacks are also supposed to appear in the objective function. So it means that the objective will be maximize Z is equal to 3x1. So we're going to have, for every inequality, we're going to have a slack or a surplus, a slack or a surplus, a slack or a surplus. So we can call them S1, S2, S3, where the S stands for either a slack or a surplus. So if we're dealing with a surplus, we take away. If we're dealing with a slack, we add. So this is 3x1 plus 5x2 plus, you keep it there. When you come to subject to, you have x1 plus 2x2. Now this is a less than sign. So if you want the left-hand side to be equal to the right-hand side, clearly you need to add something to the left-hand side, because we're saying the left-hand side is less than or equal to 2000. So for the two sides to be equal, I need to add something. So I'm going to do L plus S1 equal to 2000. So that is a slack variable. S1 is a slack variable, which we are adding to make sure that the two sides are balanced. So S1 can be 0, but can also be a positive number. It can never be negative. Then the second inequality will be x1 plus x2 is less or equal to 1500. So I want them to be equal. So again, I'm going to add something to the left-hand side. So plus S2. So S2 is also a slack variable. I do the same for the last one, which says that x2, I want it to be equal to 600. So I need to add S3. So that's how you convert the inequalities into equations. Then those slack variables, you also add them to the objective function, but you assign them coefficient 0. That ensures that the optimal solution does not change. You know, optimal solution is the best solution, so it cannot change. You cannot lower it, you cannot make it better. So you're going to have 0 S1 plus 0 S2 plus 0 S3. So that's your new objective function. Then your non-negative constraints, you will have x1 greater or equal to 0, x2 greater or equal to 0, s1 greater or equal to 0, s2 greater or equal to 0, and s3 greater or equal to 0. In other words, you can say x1, x2, s1, s2, s3 greater or equal to 0 to avoid the monotony. So this is what we call the standard form of an LP model. We call this one the standard form. The standard form. Okay. So we already know that we know the solution. We know the optimal solution already. If you don't know the optimal solution, we are supposed to solve the problem and get the optimal solution. And the optimal solution is x1 is, what do you say? X1 is 1000 and x2 is 500. So once you know the optimal solution, it is possible to calculate. So using this, using the optimal solution and the standard form of the LP model, we can easily find, we can easily calculate the values of S1, S2, and S3. Once the optimal solution is known, then it's possible to find the values of the slacks and the surpluses. Okay, remember we are trying to do what? We are trying to find how to calculate slacks, surpluses, and shadow prices. So let's start with the first equation. And usually we obtain them by solving the inequalities. I mean the constraints now, which are now equations. So working with the first equation, using the optimal values of x1 here and x2 is that, if you substitute them there, then you'll notice that the value of S1 is equal to, this will be 1000 plus 2 times 500, which is 2000. So 2000 plus S1 is equal to 2000, meaning that S1 is equal to 0. Which is okay because we say that S1 can be 0 or bigger than that. If we do the same for the second equation, we are going to have 1000 plus 500, which is 1500, plus S2 is equal to 1500, which implies that S2 is also equal to 0. It's still fine. Then we come to the last one, where we're saying x2 plus S3 is 600, and x2 is 500. So we're going to have 500 plus S3 is 600. So that means that your S3 is 600 minus 500, which is 100. Now, if the value of the slack or the surplus is equal to 0, like in these two cases, it means that the two constraints that are associated with those slacks or surpluses, the two constraints, the ones that gave us this, these two are said to be binding constraints. Those are called binding constraints. And then the other one, if the value of the slack is non-zero, you say this is a non-binding constraint. Now, a binding constraint is a constraint which passes through the optimal solution. It is a solution, these are constraints which pass through the optimal solution. If you check those two, graphs, I mean those two lines, remember, let's go up. Let's go up. The constraints we are talking about are this one and this one. These two guys. And this is our optimal point. This is our optimal solution, D. Okay. So that's what we're saying. Binding constraints have zero slacks or zero surpluses, these two. So that means this constraint here is non-binding. This one is non-binding because it doesn't pass through the optimal solution here. If it were here, the story would be different. So you see, once you solve the slacks and the surpluses, you get what we call the binding constraints. Okay. So any question there? Maybe as you ask, as you figure out about the question, we can talk about now shadow prices. So how do we calculate shadow prices? And we say that shadow prices are calculated from binding constraints. That's number one. You calculate them from binding constraints. In our case, our binding constraints are, you write those binding constraints in form of equations. Of course, now we have said that this is 0 and this is 0. So we'll end up with x1 plus x2, sorry, plus 2x2 is equal to 2000. And the other one is x1 plus x2 is equal to 1500. So what you do, you increase the right-hand side of these binding constraints by 1. So you do plus 1 there, and also plus 1 there. Then you solve the resulting equations simultaneously. Okay, you solve the resulting equations simultaneously to get new values of x1 and x2. Okay, so once you get those two new values of x1 and x2, you plug them into the objective function here. You plug them into our objective function here. Then you compare the value that you get with the value that was given by the original model. Once you get new values of x1 and x2, you plug them here, you are likely to get a new value for maximum z. Then you get the difference between those two values of z. That difference is what we call the shadow price. That difference is what we call the shadow price. So let's do that. So when you add 1 to the right-hand side of those equations, you'll end up with equations. You've just added 1 on the right-hand side. Then you solve them simultaneously. Here you'll get the value of x2 as 500. When you substitute it to one of the equations, you will get the value of x1 is 1001. So once you get these new values of x1 and x2, you are supposed to recompute your z value. Let's call it z new. Remember, Z new is given by was 3x1 plus 5x2. So we need to plug them in there. We need to plug them in there, and we compute the new value of profit. So this will be 3 times 1001 plus 5 times 500, which is 5503. Okay, so that's the new profit. Then our Z old from our original equation, 3x1 plus 5x2 was giving us 5500. Okay, this is the old one and the new one. So this one is using x1 is 1001 and x2 is 500. And this one was using what were the values? X1 is 1000 and x2 is 500. Okay, so once you do that, you get those two values. So the difference between these two, so the shadow price is Z new minus Z old. Okay, which in this case is 3 shillings. That's what we call the shadow price. Okay, so that is it about the calculation of shadow prices, the calculation of slacks and surpluses in linear programming. So that marks the end of our discussion today on linear programming. Let me know if there are any questions.